Hey everybody. So in this video, we're going to be talking about secant and cosecant graphs. So in order to introduce these, I want to begin by talking about graphs we already know, and that are sine and cosine. So when we're introducing cosecant, we're going to derive how we get that from 1 over sine. So we know with 1 over sine, this is the same thing as saying 1 divided by sine. And we know sine is the opposite leg over the hypotenuse. So when we're dividing with fractions, we are going to keep, change, and then flip this fraction. So what we have now is 1 times the hypotenuse over the opposite, and this gives us the hypotenuse over the opposite. And we know that the hypotenuse over the opposite is cosecant. Now you may say, okay, why is that useful? Well, taking the value of sine and flipping it is going to give us our values of cosecant. So we know that sine is derived from values of the unit circle. So here we have a unit circle. What we're going to do is we're going to take these y values and we're just going to flip them. So let's say if I started with an easy one, let's just say pi halves. Okay, so I took the number 1 and I'm going to say, what is 1 divided by sine, or what is 1 divided by 1, that value there? Well, that's going to be 1. So here we know that the cosecant value of pi halves is going to be 1. Now, we're going to do another easy one. What if we started at 0? So if I start right here, what is sine of 0? Well, that's going to be the y value. Well, what's the y value at 0? 0. So what's 1 divided by 0? Well, that is undefined. So how do we express an undefined value on a graph? And we do that with an asymptote. So here we are going to have an asymptote at 0. We're also going to have another asymptote at pi. Look right here. At pi, the y value is 0. Well, 1 over 0 is undefined. So here we have another asymptote. So here you should be able to recognize a pattern. Everywhere the sine function crosses the x-axis, we have an asymptote. So here we could create multiple asymptotes. So for the purpose of this, we're just talking about one period. So one period of sine is 0 to 2 pi. So for this example, we're just going to work with 0 to 2 pi. Now, let's start flipping our other sine values. So if I'm looking at pi over 6, take the y value. So here, this is 1 over sine. So this is going to be 1 over 1/2. Well, all we have to do is flip the sine value. So this is now going to be 2. So pi over 6 is the very first radian after 0. So if I come here, the very first radian, I know it's not mentioned here, but we have to plot, we're going to plot 3 points. So I'm going to start at pi over 6. I'm going to be really close to 0, and I'm going to go up to 2. That's what that value is going to be. Now, let's look in between 0 and pi halves at pi fourths. So here, this is now going to be 2 over root 2 because we're flipping the y value. Well, I don't know what that is, so let's go to our calculator and say that. What is 2 divided by the square root of 2? And we get 1.4. So here, right in the middle, we're going to go up to 1, and we're going to go just past it, almost at 1.5. So now we can come back to our unit circle at pi thirds. Here we're looking at 2 divided by root 3. So here we have 2 divided by the square root of 3. Let's clear all this. So here 2 divided by the square root of 3, and that gives us 1.15. So this is even closer to 1. So right here, we're even closer to 1. And then we know at pi halves we are at 1. Now let's look past pi halves. So if I look past pi halves right here, oh, look, 2 divided by root 3. Well, we just did that at pi thirds. So here, we could be just above that. And at 3 pi fourths, that's the same thing we got for pi over 4. So that's this dot right here. That was like 1.4. And then at 5 pi over 6, very close to pi, that's the same answer we got as pi over 6. So that was going to be 2. So now look at what my graph does. My graph is approaching the asymptotes on either side. Now look at the sine function. The sine function is positive, and then the cosecant function is going up. So now let's see what happens when the sine function is negative. So we can start with an easy one, 3 pi halves. So I've come right here, 3 pi halves. This is, what's 1, right? 1 over the sine value. What's 1 divided by negative 1? Well, that's just going to be negative 1. And now I'm going to pick values from pi to 3 pi halves. So if I start right here, 7 pi over 6, and I flip this, that's negative 2. So right here, I come down to negative 2. And then if I start right here, this is negative root 2 over 2. So the cosecant value is going to be 2 divided by root 2. So here, this would just be 2 divided by root 2. And we know that's going to be negative because we were making this a negative. So it's negative 1.4. So here, negative 1.4. And you can kind of see already that we're doing the same thing this one is. It's just flipped downward. So here, I could take this and I could flip it downward like this. And this would be 1 period of cosecant. So this is why the graph looks like this. Because when we graph it in Desmos, let's do that really quickly. So here, if we graph the cosecant, and we'll just say here of x, look at this graph. So notice how this graph here looks very similar to mine. Now, we could even include our little dotted graph and just say, what's sine of x? And here, we're going to hold this down, and we're going to make this negative. Or not negative, we're going to make it dotted. So now we've almost created the exact same thing. So here's my sine graph, and here's why cosecant opens down the way that it does. Now, the process is the exact same for secant, except the only difference is with secant, you're working with a cosine graph. So I'll give you a minute. You already have these notes. You can pause and you can try this one, but you'll notice the exact same occurrence. Everywhere cosine crosses the x-axis, you have an asymptote, and then everywhere cosine is positive, the graph is going to open up, and everywhere cosine is negative, the graph will open down for the reciprocal function. Okay, here on these examples, they've already provided us with graphs, and now what we want are the key components of those graphs. So you notice we have the exact same equations we did for sine and cosine. The only difference now is secant and cosecant. So this is literally going to be the hardest part, remembering which trig function you are working with. Secant, this is cosine. And cosecant, this is sine. Now, I know this is where everybody gets confused that I've taught this for years. Everybody thinks, oh, secant, S, oh, that means sine. No, right? Remember reciprocals, you flip, you're kind of doing the opposite, you know? So think, oh, S, oh, I think sine, but it's not. It's the opposite. It's cosine. Oh, the C, I think cosine, but it's not. It's the opposite, sine. So here, reciprocal functions, these do not have a amplitude. These, now the A is going to represent the vertical stretch or compress. Here, remember that this is the oscillation speed. This is how fast or the frequency of the graph. So this is not the period. The way we find the period is 2 pi over b. C is still the same with my phase shift. D is still the same with my vertical shift. All right, so let's take a look at number 1. Find the parameters of each secant, cosecant graph and determine a possible equation. So here they tell us use cosecant. So if we are using cosecant, that means this dotted graph is a sine function. Okay? So we're going to treat this the same way we always have. The first thing we're going to identify is the midline. So here we are going to draw a line for our midline. So we have that here. All right. So the midline is always going to represent the vertical shift. So if my midline is on -2, that is my vertical shift. The period is how long it takes it to complete one cycle. So here, if I started here, remember sine goes up, down to the midline, down, back up to the midline. So this period is 2 pi. The vertical stretch and compress, this is the same value as the amplitude, but with reciprocals, we do not call it the amplitude. We call it the vertical stretch or compress. So here, this would be 1, 2, 3. And if we want to, because this is larger than 1, this would technically be called a stretch. And now we have to find the phase shift. Okay, so the easiest way to find the phase shift with sine is you start at a crest and you fall back to the midline, right? The actual definition is you look at a crest and here you look at a minimum and you see where they meet in the middle, but they'll always meet on the midline. So I always tell my students, crest, fall back. So crest for sine, fall back to the midline, and that x value is 0. So here, for my possible equation, I could say y equals 3. I am using cosecant, so that is CSC. That is so important because if you write sine, you are wrong. We are not trying to graph a sine function. We're writing the equation for a reciprocal function. So we have to use the reciprocal identities here. So 3 cosecant, and then the period is 2 pi. Now, that's not the frequency. The frequency is 2 pi over the period. So here we could say 2 pi over 2 pi. And now we have x minus the phase shift of 0, and then apply our vertical shift. So if we wanted to simplify this, we could say y equals 3 cosecant x minus, well, you don't really have to say x minus 0. We could just say x here. Minus 2. There we go. So it's no different than working with a sine graph. So let's try one working with a cosine graph. So if we want a cosine graph, we are looking for secant, right? So all of these are examples doing exactly what I just did. You're working with a sine function to find the components. Here, let's work with a cosine function to find the components. So the same thing, I'm still going to draw my midline. So here I have my midline. This midline is at -1. So that's my vertical shift. The vertical stretch or compress is going to be the same value as the amplitude. So -1 to 1 is 2. So this is going to be a stretch. The period is how long it takes it to complete a full cycle. So remember, you can always measure that from crest to crest. So here that value is 1. And then the phase shift with cosine, remember, that's the easiest one. So the phase shift of any cosine is going to be the x value of any crest. So here I could say 0 or I could say 1. So here we'll say 0. So a possible equation here, we have y equals 2 secant. So we're not going to say 1. Remember, this is the period. So the answer, or excuse me, the frequency is 2 pi over the period. So this would be 2 pi over 1, x minus 0 minus 1. So if I wanted to simplify this, clean it up a little, I have 2 secant 2 pi x minus 1. And that would be my equation. So in the notes, you have various examples doing this. They're all the exact same. So you're either working with a sine or a cosine graph. And the way you find those values here, these key components, all we're referencing is that dotted line for that original trig value. Okay? What if we started here? What if we don't have a dotted line? That's fine. We can still work on this. So remember, the easiest one to find is the midline. Okay, well, what number is in between -6 and 2? Okay, so if you like the dotted line, you're more than welcome to draw one. So here we could draw a dotted line. Right? So I'm thinking, okay, -6 and 2. What's that total distance? Well, that total distance is 8. Okay, what's half of 8? And that's 4. Now, the midline is not 4. The midline is going to be 4 values above -6 or 4 values below 2. So my midline here is actually going to be at -2. So here, this is my midline. at -2. So that's my vertical shift. So my vertical stretch or compress, how far is this crest from the midline? Well, if this is -2 and that's 2, we just found it, 4. The period is crest to crest. So here we don't have two crests. All we have is a crest and a minimum. Okay, well, if crest to crest is the period, then crest to a minimum is half the period. So think about this. How far did I travel from 4 to -4? Well, that's 8, and that's half. So the period is just 16. You could also measure it asymptote to asymptote. So -8 to 8 would also give you the 16. So this is secant. That means this dotted line is cosine, and we're looking for a phase shift. The phase shift is any max of that cosine graph. So that x value here is 4. So now we have y equals 4 secant 2 pi over the period, phase shift, and -2. So now we're going to clean this up. We will just reduce a little. 4 secant here. This is going to give us pi over 8, x minus 4 minus 2. And there we go. That is it. That is all we have to do in order to write an equation for a reciprocal identity. Now, in these notes, there are examples. We're going to get to these. There are 4 examples where you can graph. You're not going to have to graph in the homework. You're also not going to have to graph on the quiz or the test. We don't really graph reciprocal identities very much anymore. So for the purpose of this exercise, don't worry about these. So we can easily do these. Here they give you the equation and they say, from the equation, can you derive these key components? And of course we can. The vertical stretch or compress, that's this value here. Now, is that a stretch or compress? That's a stretch. Now, we haven't worked with an example where it would be a compression. A compression, let's write this out. So a compression would be if that value were larger than 0, but smaller than 1. So we're talking about decimals and fractions. Okay? So the period. This equation is not even written in standard form, right? So here we need to write this in standard form. So we have 3 secant, and we're going to pull out the greatest common factor here. So we have 2x minus 3 plus 1. Now, we like this. Remember, you say, okay, how do I know this is standard form? This is coming back from that equation we saw at the very beginning right here. So these are your reciprocal identities in standard form. I always tell my students, we want those 2 parentheses. We want the frequency. We want the phase shift. We want the vertical shift. We want A. We want to see all 4 numbers. So if I come back to my example here, now we're back to seeing all 4 numbers. So there's my stretch. The period is 2 pi over the frequency. So this is 2 pi over 2, or just pi. The phase shift right here is always going to be the opposite of what you see in the equation. So the phase shift is 3, you're not wrong, but what direction? And that will be to the right. That's why I say the opposite, because people see that -3 and they think, oh, to the left. Okay, well, the equation, the standard form is x minus the phase shift. So x minus 3, 3 being positive, right? 3 to the right, that's how I get x minus this. If it were, say, -3, it would be x minus -3. That makes you think, oh, that went to the left. Well, the 2 negatives give you a positive. So inside, if it said x plus 3, that means it goes to the left. And then my vertical shift is just my last number here at 1. And that is it. Those are your components from a trig graph and from an equation. That is all you will need to complete this homework. Try a few of these on your own before starting the homework. If you have any questions, let me know. All right. Bye, everybody.